We need to talk about forces now. A force is an interaction between two objects. It's how they communicate. It's a push or a pull, but it results from two objects interacting with one another. A force can change the motion of an object. So we say a force causes acceleration. And this is how we derive our kinematics equations. Forces can also change energy through work. Work is equal to a change in energy, and it's equal to a force times a distance, dx. I'll just leave it as a small distance for now, because if a force is not constant, we have to integrate, and that's why we write it as dx. But force times distance. And I'm going to write it with that dot product, which we'll learn how to deal with shortly. Forces can also change momentum. So we call that impulse. That's equal to a change in momentum. We use lowercase p for momentum. And that's the force multiplied by some time interval. So forces can cause changes in motion, or we call that acceleration. That leads to our kinematics equations. They can change the energy of our system. We can calculate that through the work done. And they can change the momentum of an object. We can calculate that through the impulse. Let's take a closer look at F equals ma. Let's say I have a cart moving to the right with a speed of 1 meter per second at t equals 0. 1 second later, my cart is at rest. And 1 second after that, it's moving to the left with a speed of 1 meter per second. Well, what do you know about this cart? There must be a force pushing it to the left. Some kind of a force pushing on it in this direction that's causing it to slow down between t equals 0 and t equals 1. And that same force is acting on it at all times, because between t equals 1 and t equals 2, it speeds up. But it's always experiencing acceleration to the left. So we'd be looking for, I don't know, a rope or some kind of a mechanism for delivering a force to this cart that would cause its motion to change like this. If there was no force acting on that cart, it would keep moving with the same speed in the same direction forever. It would never change. But because its motion is changing, we know there's a force acting on it. And we can figure out what that force is using F equals ma. So the mass of our object, well, we'd have to know the mass of our object. Let's make it a 10 kilogram cart. And what's our acceleration here? Our object is moving at 1 meter per second, and then it's at 0 1 second later. So its velocity changed by 1 meter per second in 1 second. So its acceleration is 1 meter per second per second. Change in velocity over time, or 1 meter per second squared is typically how we would say acceleration. So this is a force of 10 kilogram meters per second squared. And we get tired of writing kilogram meters per second squared all the time, so we call that a Newton. 10 newtons of force acting on our cart would cause this motion. I think now's a good time to talk about our conservation laws, energy conservation and momentum conservation. We've been using the terminology energy conservation and momentum conservation. What does that mean? It means the energy does not change, the momentum does not change, and we can use that to help us solve problems. But now I'm telling you that forces can change energy, forces can change momentum. So when is energy conserved, and when is momentum conserved, and when isn't it? Well, When we have forces reaching into our system, they can change the energy of our system. If I have a couple of objects here, a boundary around them, and I say, this is my system. If I don't allow things to reach into my system, if I don't add energy to the system, how can I add energy to the system? Well, in a number of ways. I could heat it up. Those are candles. If you haven't realized it by now, I can't draw. Okay, we can add heat, right? We can add some energy through heat. Or we can reach into the system. We can reach in and exert a force. I can reach in with my hand and push on that box and change the energy that's in the system. There's now more kinetic energy in the system. So those are two ways that we can add energy. We can add heat to the system. We can reach in and with a force, an external force, and do work on the system, adding energy to the system. So in those cases, energy is not conserved for our system. Now, if I include the candles in my system, if I erase this boundary and draw a new boundary, I'll use red for my new boundary. Now, with my new boundary, energy is conserved. I could calculate the chemical energy in the candle and figure out how much of that is going into the system and changing the system's energy, but the candle would be losing its chemical energy as my particles, my objects, move faster or gain energy. So if I include everything in my system, if nothing reaches across that system boundary, then energy is conserved. If I'm allowing energy to flow in or out, or external forces to come in or out, then energy is not conserved. So I could reach in with my hand and push, exert a force, and energy would not be conserved for this system because I have some external force coming in, the force that my hand is providing. If I include my hand and body in the system, if I draw a new system boundary, perhaps I could calculate the stored potential chemical energy in my body and how that gets converted through a force, through my muscles, pushing, applying a force to my objects, and turned into kinetic energy. And then I could say energy is conserved. The same is true for momentum. As long as there's no net force acting on our system, then the momentum of our system remains the same. It's conserved. So let's look at an example. Maybe we drop an object. We're holding an object in our hand and we drop it. Maybe it's a basketball and we drop it. It starts out at v equals 0 when we let go of it. And at some later time, it's moving at some high speed, right? It moves faster and faster and faster as it falls. And then it hits the ground and comes to rest again. So its momentum is clearly not the same. Something is changing the momentum. Well, that's because if we draw our system boundary as just the ball, we have an external force reaching in, pulling on it. That's the force of gravity reaching into our system. So our system has a net force. So momentum will not be conserved in this case. But if we include the Earth, if we get rid of this boundary, and we include the Earth in our system, and we draw a new system boundary, then there is no net force. The Earth pulls on the ball, and the ball pulls on the Earth with an equal and opposite force. They are interacting with each other. Anytime two objects interact with each other, they feel the exact same force. It's just in the opposite direction, right? Because if object A is pulling on object B, then object B has to be pulling on object A, and the forces would be toward each other. If they were pushing on each other, they would be away from each other. So always in opposite directions, and always the same magnitude. In this case, There are no external forces, no forces reaching across that red dashed line. All of the forces are internal to the system. So now momentum would be conserved. There's a problem though, and that is that the Earth is huge. For most of our calculations, we're dealing with boxes and people and cars and things that aren't that big when we compare them to the Earth. And so the Earth is almost acts like it has infinite mass. It's really not going to move at all. When we let go of the ball and it starts rushing toward the Earth isn't going to rush up toward the ball, is it? Because it's so much more massive. So anytime the Earth is involved, it really messes up momentum, and we have to use other techniques. Even though technically momentum is conserved when we include the Earth in our system, from a practical standpoint, because the Earth is so much more massive than our other objects, it just doesn't work in our calculations. It's almost infinite mass compared to our other objects. So let's take a look where the objects aren't the Earth. Let's have a cart and another cart, and then maybe a person sitting here. And then the person is going to push off with their legs. They're going to push on cart A. And what's going to happen? So let's say nothing is moving right now. Nothing is moving. And then our person kicks and pushes on A. And what's going to happen? So A is going to move to the left. B is going to move to the right. Now, let's pretend for a minute we chose our system to be just cart A. Can we use momentum conservation to calculate what's happening with cart A? No, because a force comes in, crosses that boundary from the person's foot and pushes on it. So this isn't going to work. We do not have a net zero force in our system if that's our boundary. But what if we choose this as our boundary? What if we choose both carts and the person? Everything is in the system. So now nothing crosses that boundary. All the forces are internal to the system. Now we can use momentum conservation to calculate what's going on. In the first case, we had our initial momentum was 0 because nothing's moving. That means that at the end, our final momentum also has to be 0. And now, if we knew a little something about these carts, if we knew the masses of the carts and the person, and maybe one of the velocities, then we could solve for the other one. And finally, let's talk about units. Work has the same units as energy. It's a force times a distance. So what do we get? For our force, we have newtons. And for a distance, we have meters. So a Newton meter. Of course, a Newton is really a kilogram meter per second squared because we know F equals ma. So we have a kilogram meter squared per second squared. And we get tired of writing Newton meters, and we get tired of writing kilogram meters squared per second squared, so we write that capital J, a joule. That's 1 joule of energy is equal to a kilogram meter squared per second squared, or a Newton meter. And that has the same units for work and for energy. The units are joules. For momentum, we've got force times time. We've got Newton seconds. And what is a Newton? A Newton is a kilogram meter per second squared. When we multiply by seconds, it cancels one of them, and we get kilogram meters per second. We get mass times velocity, which is correct for momentum. For some reason, we never get tired of writing kilogram meters per second for momentum. There's no special unit for momentum. The units for momentum and impulse are kilogram meters per second.